Okay, so linear versus nonlinear functions. A linear function is a function that will make a blank blank when it is graphed. What do y'all think goes there?
Straight line.
Straight line. An equation is linear if it can be written in the form of
y equals mx plus b.
y equals mx plus b, where m is the slope and b is the, look at y'all. Y'all probably could do this whole lesson by yourselves. The table is linear if it shows a blank rate of change throughout the entire table.
Constant.
Okie dokie. In the following examples, we'll use the functions to fill out a table of values and then create a graph. Look for any patterns among the functions that are linear and those that are not. So our job right now for the next 2 minutes is to complete this table, this graph, this table, this graph, and then I will come back and we will answer these. So I'm going to give you 2 minutes. Go. Okay, what did y'all get for, I left my pen. Hold that thought. Okay, what did you get for when the input of -2 goes into the rule, you get what for the y? Positive 5. Because -2 times -2 is 4, 4 plus 1 is 5. Yes? Why am I getting a bunch of O's?
I thought it was positive 2.
Okay, ready? -1 times -1 plus 2 is going to give me what? 2. 0 times 0 plus 1. 1 times 1 plus 2. I'm sorry, plus 1.
2.
Sorry, I gave you the answer. 2 times 2 plus 1 is 5. So when we graph him, he's going to look like what? -2, 5. -1, 2. He looks like this. Yes? Okay. Now let's go to the next one. -4, when plugged into this equation, is going to give me what?
-2.
What about -2?
-1.
0,
0.
2,
1.
4.
2.
And if we graph that, it looks like this. Right? Okay, so is this function linear? This one. Why not?
Non-straight line.
Okay, so not a linear function. Because not a straight line. And what can you tell me about the table? What were the rules? Go to the top.
One input.
Go to the top. A linear function is a function that will make a straight line when it is graphed. An equation is linear if it can be written in the form of y equals mx plus b. The table is linear if it shows a constant rate of change throughout the entire table. So, is the function linear? Why or why not? It's not a linear function because it's not a straight line. And the table what?
Doesn't have a constant.
Does not have a constant rate of change. Okay, what about the next one?
Yes.
Is it linear?
Yes.
Yes. Why?
Have a straight line.
The graph is a straight line. And what?
Has a constant rate.
The table has a what?
Constant rate.
Constant rate of change. What do you notice that is different about the functions in questions 1 and 2? What do y'all notice about the difference between the functions in 1 and 2? I want you to look at the actual equations.
One's written
I'm good. I went. Thank you. I'll wait. I don't have to give you an answer. I can just wait for you to actually look and put in some effort and see what happens when you try. I have a whole 45 minutes left to teach this class. Thank you, Miss Amy. Look at the difference between them. What you got, Madison? Number one has an extra what? Oh, it has a +1. Okay, cool. But they both have a y-intercept. One's just 0, the other one's 1. So they both have a y-intercept. Okay, anything else? Yes, ma'am. The first one, x is squared, okay? Here's x is squared. Y'all see that? Okay, anything else? What? What has no slope? Question 1 has no slope. She's saying there's no rate of change. Would y'all agree or disagree? Okay, so let's look at it. The first equation has no constant rate of change. And the second one does. Also, the x variable is raised to the what power? The exponent is greater than 1, which keeps our equation from being linear. Anybody know what kind of equation that is? It is nonlinear, but do y'all know the math term for it?
Undefined.
No. It's called a quadratic. You don't need to know that. I'm just asking if anybody did know it. It's a quadratic equation. That's why it makes the U. Anybody know what the U is called?
U.
In math terms? It's called a parabola. Some people say parabola, but that sounds really funny. It's a parabola. Spelled this way. Parabola. You don't have to write this down. It's a parabola of a quadratic equation. You're going to learn that next year in algebra. Guarantee it. And you're going to use it in algebra 2 as well. Okay, ready? Here we go. I just got a letter. I just got a letter. I really got an email. Wonder who it's from. Okay, here we go. I could be a kindergarten teacher, 100%. But it's way more fun to be a middle school teacher and act all crazy because y'all don't like it. Y'all just make fun of it. Okay, here we go. So, what we're going to do is we are going to do number 3, 4, and 5. I'm going to give you 5 minutes to work through them, and then we're going to come back and talk about if they're a function or not a function. So, you're going to fill out the table and the graph. Go. So, we input in -2 into this equation. So, that means that -2 is being cubed. -2 times -2 times -2 is going to give me what? -8. Okay, -1 times -1 times -1 is going to give me what? 0 times 0 times 0. 1 times 1 times 1. 2 times 2 times 2. 8. Okay, if we graph this, we're gonna get -2, 8, -1, 1, 0, 0, 1, 1, 2, 8. Okay, is this a linear function? I'm sorry?
-8. For negative, you put it -8.
Oh, I'm sorry. And -1, -1. My bad. So it should look like, this is how weird this one looks. Okay? Is it a linear function? No, it's not a linear function. Why? The graph is not what? And the table has no what? Constant rate of change. Okay, number 4. If you input 4 into the rule, what do you get as your output? -4. -2? 0? 2. 4? -4, 4, -4, -4. Right here, -2, -1, 0, 2, 2, 5, 4, 8. Like that. Yes? Is this a linear function? Yes. How do you know? Graph is a straight line. And it has a constant rate of change. Okay. Number 5. 1 what? 12. 2 what?
6.
3? 4?
3.
6?
2.
Okay. If we graph it, 1, 12. 2, 6. 3, 4. That looks weird. 4, 3. 6, 2. Huh. Interesting. Is this a linear function?
No.
The graph is not a straight line. And what can you tell me about the table? Okay, what differences did you notice about the equations that were linear functions and those that were not?
Linear.
What were the differences?
Linear functions are straight and non-linear functions.
We're talking about the equations. What did you notice about the equations that were linear and the ones that were not? Yes, sir.
Linear would be
What? Okay. Josie. Can we go a little bit deeper than that, though? They have a y-intercept, but what form are they in? Linear equations are in y equals mx plus b form. Non-linear equations are what? Wonderful, non-linear equations. Let's go into a little bit more detail.
non-linear equations aren't like. All they have is a slope and a line or so.
They don't have a mean. They're right.
The what? What'd you say, Priya? Not necessarily. Everybody look at the top 3 equations, please. What did we notice about the one equation that was linear? It was in what? What do you know about the other 2 equations? They don't have what? They don't have a constant rate. What else? What? What form are they in?
Just
Not necessarily.
Y equals
There's no slope. What's different about the equation in the middle compared to the other two equations on the outside? That we already said there's no slope. That's the constant rate. Yes. This is the time where you think and stop looking at your neighbor across the table making funny faces at them. Try. See what happens. You're looking for what is different. You've already told me that the one in the middle is in y equals mx plus b format, which means that the other two are not in y equals mx plus b format. But what does that mean? What does this one have that this one doesn't have?
exponent.
Thank you. So they also have an exponent greater than 1. What else do they have?
Fraction. Well, no.
Or what's the fraction?
12 over x.
What's in the fraction? Huh? X is in the what? As the denominator. Question, what's its exponent right now?
But
What's its exponent right now? 1. What would happen if we wrote it in the positive? Right now, it's a 1 to the denominator. When we learned about exponents, and it was in the denominator as a positive, that means that it would be in the numerator as a what? Negative. So this is actually y equals 12 times x to the negative first power. Correct? Am I making that up? No? Okay, so if x is in the what? Denominator, if x is in the denominator, it's also not a function because one over x is the same thing as x to the negative first power, which also means that your exponent is not not a 1. Is it? It's a negative 1. Great crowd. Okay, what differences do you notice about the tables?
all the nonlinear
Non-linear doesn't have a what?
like the line percent.
I see it crossing the y-axis all the time. There's a y-axis cross. This one's gonna cross somewhere down up there. Non-linear what? Non-linear tables what? Do not have a constant rate of change. What about linears?
Linears do have a constant rate of change.
So I'm going to give you 2 minutes to summarize this part of the lesson. Summarize this part of the lesson. That means you're going to write 2 sentences. Go. Okay, who would like to share their summary? Trevor.
Today in this lesson, we learned how to find out if the graphs are linear or nonlinear. Also, compare the two to see the difference.
Okay. Anybody else? Camille, can you share me yours, please? Define it. Okay, so how would you define it? Okay. Okay. Awesome. So turn to page 3 is your homework. So write homework on there. And then turn to the next page where it says handout 6. So we're going to analyze our functions and our graphs. Okay, there's 2 ways that we can analyze parts of a function. The first way that we can analyze the part of the function is describe them as increasing or as decreasing. Increasing means to go what? Up. Decreasing means to go down. I'm so glad we know that. Okay? And the other way that we can classify them is exactly like we just learned. So what's the first way?
Linear.
Linear or non-linear. Okay, linear or non-linear. So we're going to kind of talk through and try to figure out the parts of this function shown below. They want us to look between x equals 0 and x equals 4. So when x is 0 and x is 4, we want to know what does this line show. So is it increasing or decreasing? Increasing. Is it linear or non-linear? Oh, really? Look at it. Linear or non-linear? Why non-linear? Because look, at this point it does what? It curves. Okay? Now they want us to look between x equals 4 and x equals 8. So now we're going this way. Increasing or decreasing?
Decreasing.
Linear or non-linear? Okay, so a distance versus time graph shows us how far 2 objects are from one another. Consider what the following types of lines on a distance versus time graph would represent. Okay, ready? I need one volunteer that's willing to walk across the classroom. Come on, Ace. Start at the door. Ace is starting at the beginning. I'm going to time him as he moves at a constant rate to the other side of the classroom. This is the beginning of the distance. This is the end of the distance. We're moving at a constant rate of what? Change. Okay, ready? Constant rate. Timing. Go. Fantastic. Can you explain to me what just happened? Was he moving away from the beginning or closer to the beginning? Away. So, I'm going to use Ace's name. Ace was moving away at a constant speed. Okay, what would happen if I asked Ace to walk back to the door?
He would go closer to the beginning.
Okay, good job. Ace was moving closer at a what? A constant speed. Because linear means that it's moving at a constant what?
Rate.
Stop. Face them. Okay, everybody look at C. This is what Ace is doing. Explain to me what's happening.
In the middle.
What's that mean, in the middle?
Not moving.
He's what?
Going in a straight line. Like,
What do you mean he's going, is he going in a straight line right now? He is at a what? He's at rest, he's not moving over a certain amount of what? Time. Do y'all see what's happening? Okay, thank you. Ace was at rest and not changing his distance. He didn't go anywhere. The only thing that changed was the time. It's kind of like when Ms. Gode just holds the pin here. Nothing's happening. It's just kind of hanging out. The only way it's going to happen is if I throw it up in the air or I drop it. Other than that, it's not moving, right? It's not going anywhere. It's staying right there until I decide that I want to drop it or throw it. Got it? So, the time can just go on and 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 on, but the distance of this is not moving from the ground. Unless my arm gets tired. Yeah? Okay. So, I want you to understand that A represents that we're moving away at a constant speed, we're moving closer at a constant speed, or we're not changing at all. Okay, let's look at the next one. D. What could explain this one?
like,
Yeah, exactly. The object is moving away. And increases speed. I can't spell today. It's okay though. Okay, what's happening with E?
starts off fast and goes slow.
Okay, so the object is what? Remember, we're trying to figure out if it's going away or coming closer. So the object is what? Moving away. What's happening to the speed? It's what? And decreasing speed. Do y'all see how it's just starting to slow down? Okay, turn the page. Now we're going to match each distance versus time graph with the correct description. Now listen, the way that we're going to explain this is, are we moving away, closer to, are we stopping, standing still, what's happening? So everybody look at A. Kaylee got on a bus at her house. The bus made 2 more stops before it arrived at the school. So, let's look at the first one. What's happening in the first graph?
Increasing quickly.
We're going away at a what? Constant rate. Then we what? Stopped. And then we did what? Kept going. Okay? What happened in B? Or this one? We went, then what happened? Stopped, then we went, then we stopped, then we... Okay? What happened to this one?
Went up and then decreased.
Wait. We went up and then we went all the way what?
Down.
We went all the way back, right? Then we went all the way forward. Yes? Okay, so which one does A match?
Middle.
The middle one, okay? Let's read the next sentence. Brennan and his dad left for school in his dad's car. They got stopped by the train tracks for several minutes before they were able to continue to school. This one or this one?
B.
B. This one? First one or last one? First, okay? Even though you know C, let's read it because I want you to see something. Cameron left for school with his mom, but remembered he left his English project at home. A lot of you could probably relate to this. You forgot something at home. What she did, she either said, oh well, and brought you to school, or she did what? Went all the way back home to pick up whatever it is that you left, and then drove you to school. So let's look at that looks like. She took him back home to get his project and then headed back to school. Ready? So she went forward, went all the way back, and then brought him to school. Do y'all see that?
Yeah.
Because the distance went all the way back to the beginning. Now we're going to create a graph. Adam left his friend Brody's house and started walking home. So, where are we starting at distance?
At the beginning here.
Right here? Why there? That's his house.
Because you just left.
Look what it says. Away from his home. So are we moving away from his house or closer to his house?
So you're decreasing.
Are we increasing or are we decreasing? Why are we decreasing?
Because he's less than his house.
We're getting closer to his house. So that means we're going to start somewhere up here. Yes? Okay. Adam realized that he left his phone at Brody's house. So he's going down. What does he have to do now?
Go back up.
Go all the way back up. Adam left Brody's the second time and started to walk home. What are we doing?
Go back down.
Okay? Adam stopped halfway to do what? So what kind of line am I going to have now?
Straight.
Like this?
Yes.
Okay, now what happened? He quickly ran home. What does it mean quickly?
Means you go up fast.
We went up fast?
Down.
So that means we need a what kind of line? A steeper line. It can't be straight. He's not falling off the line. He's just going steeper. Okay, let's look at number 3. Vanessa left her house to run at a steady jogging pace. What's that going to look like?
It's going to be increasing.
Out of what?
So 0.
0, 0, and we're going to go at a what? Constant rate. So that means that she's going at a pretty decent pace. Then what happens?
And that's an increase your speed halfway. You gotta wait.
Okay, wait. So we got to increase her speed. What happens?
She goes up, and then she goes to.
It's more steep. Then what happens?
She got a leg cramp.
She got a leg cramp. So what she did? Stop. So what's that look like?
Just straight.
Okay. Then what happened?
And she sat down.
That's that part. Then what happened? Okay, out of what? Out of what?
Much slower pace.
Okay, if we have a much slower pace, are we going to have a steep line or a not steep line?
Steep line.
Not steep line. So it should kind of look like this. Yes? Okay, pay attention to the details. Look at number 4. The graph below shows Justin's distance from his house as he walks to school. Interpret what you think happened at each segment of the graph. Go. Okay, who wants to share their story with me? Who wants to share their story? Okay. What? What? You have to wait a minute. Okay, share the story. Trevor, what you got?
Justin walked to school at a constant speed.
Okay.
He stops to talk to his friend, and then after he talks to a friend, he walks back to school at a constant speed as well.
That's a constant speed?
Yeah.
Huh.
Well, he
Anybody have a different story? What you got, Lola?
I put Justin took off to school from his house, stopped to check his time, then started back up at a faster rate, realizing he was
Okay, realizing he was gonna be late, okay. But that would just mean that he would be going at a linear, right? Is this linear? No, okay. So, what you got, Ray?
Justin is walking through the woods. He hears a sound and stops to look around. He continues walking, but gets faster as he hears the sound getting louder.
Okay, but that's still constant rate of speed. What you got, Mackenzie?
Justin was walking to school, talked about vacancy, walking at uneven speed.
Okay. What you got, Ace?
He was jogging. He was in a jogging pace. He stopped for a little bit to get ice cream and went on and started to pick up speed over time.
Okay, I have a question. Can you turn the page over, please, and look at these two graphs? What's a way that he can increase in speed? Because that's what this graph looks like, right? What's another way that he could increase in speed?
Jogging and then he was sprinting.
He what? Okay, walking and started running. Where's the only thing that you get in or get on that would increase in speed? A car or a bike or a
Wheelchair.
bus or a wheelchair. Sure. Okay, so what happens if he had a friend like Trevor and he jumped on the back of his wheelchair and they took off riding?
I don't know what Justin's.
I'm just saying. Okay, so think about it this way. Justin's walking to school. He stops to tie his shoe real quick. His buddy sees him on the side of the road. He's like, hey, buddy, you need a ride? And he gets in the car, and then they take off and go to school. Could that be an option? Okay, so what you're going to do